Hi, welcome to Ordinary Differential Equations. Today we are going to continue our discussion about Laplace transform. So you remember that last time we explained what Laplace transform is. It is a product, integral of a product of a so-called kernel with our function. The kernel is a function of a new variable s. We integrate this product over 0 to infinity, and the result's called the Laplace transform of the original function. We went after some basic functions, constants, exponentials, polynomials, sine and cosine hyperbolic, and trigonometric, the circular sine and cosine. We found the formula for each of these cases. Each of them have some kind of a restriction on s. We had one simple rule regarding linearity. If you have a sum order difference of two functions, then the Laplace transform is just made out of sum order difference of the two Laplace transforms. If you multiply each of your functions by a constant, you also multiply the Laplace transform by that constant. The notation for inverse Laplace transform, that's when you have the item on the right hand side and you want to write the item on the left hand side, is script L inverse of capital F is a little f. For today, we are going to aim at some high level type of formulas. Formula number one is considering the following. What if you take an exponential and multiply by some function that you have in your table? Can you figure out what the Laplace transform of that one would be? And we have a very simple formula for that case. Next formula is what if you have a polynomial multiplied by some function that is in your table. This one is also doable, a little bit more complicated than the previous one. We are going to talk about that. There is a longer list of these transform formulas. We might come across some of them. Some of them you are going to see in your exercises. You have to build them from scratch. But two extremely important formulas that we are going to talk about today is what's a Laplace transform of a derivative of a function that happens to be in our table. So we are going to look at Laplace transform of, say, f prime or f double prime, and we are going to find the corresponding formulas for them. So let's go after the first of these things, which is the very easy one. So here the idea is the following. Suppose I have a function f of t, some function that happens to be in my table, and then I multiply it by some exponential, like exponential of 2t or 3t or in general at, and I want to find the Laplace transform of this. Well, you have to start from scratch, that is, use the definition. This is integral from 0 to infinity of the kernel. Kernel always exponential of minus st times whatever function you have here, which is exponential of at f of t dt. I combine the two exponentials, I get exponential of minus st plus at f of t dt. Well, what can I do? Well, of course, I can factor a t here. So let's write this thing as 0 to infinity of exponential of. So I put a factor of t. To imitate the general formula, let me also factor a minus. And then in the parentheses, I will have s minus a, f of t dt. Now, carefully look at what we have and compare it against the definition. For f of s, we had integral from 0 to infinity of exponential of minus st f of t dt. So what's the difference between these two cases? The difference is that here I have s minus a, and here I have s. So stands to reason if the final output of this integral is f of that s, that is f of whatever is inside of that box, then in this case what we are going to have is f of, that's going to be f of, so all we are going to do is simple substitution. Instead of s, I have s minus a. So that was simple enough, rather magical that we get it so easily. Now let's go ahead, practice it to make sure we understand what is it that we are talking about here. Let me just remind you, for example, suppose I have already studied what is Laplace transform of cosine of 3t. Is that right? We have done this thing last time. And well, for cosine, we have already made formula here. So it is s over s squared plus 3 squared. Now the question is, what if I multiply this thing by exponential of 2t and take the Laplace transform of that? Well, this is saying you're going to do a very simple thing. You're going to do a substitution that s is going to be replaced by s minus whatever this coefficient is. So instead of s, I will have s minus 2 over, again here to do substitution here as well, plus 3 squared. So as simple as that, when we say f of s minus a, it simply means whatever formula you had before, the s of that formula is going to be replaced by s minus whatever this number is. Now, in most applications, we deal with a decaying exponential. A decaying exponential indicates that in our physical problem, there is a friction or damping or something to that effect, that the signal dies as time passes on. That's a very common kind of a function that comes across in many applications with oscillation and problems of that nature. So what happens when I have an exponential of a negative? Well, simply we have to replace s by s minus this number. So it's going to be s minus minus 2. S minus minus 2 squared plus 3 squared. So of course, once we get used to it, we just write it in a more readable form, and that is our answer in this case. Same thing applies. Let's do another example. Suppose I do exponential of minus 3t times t to power of 5. Suppose I want to find that. Well, I start with what was Laplace transform of t to power of 5? You remember it was the factorial of this number over s to power of 1 larger than x6, 5 plus 1. So what do I have to do? Instead of s, so I copy everything that I had. Instead of s, I'll have s minus multiple of t here. So that one has to be raised to power of 6. And of course, we clean it up and write it as s plus 3 to power of 6. So from now on, if we have a negative for the coefficient of the exponent of exponential, then we just have s plus that number. So that was an example of a polynomial, and we had an example of this one. You can also write exact same thing with sine or cosine hyperbolic. So we have we have dealt with this case. Now let's go after the next one. What if I have a polynomial multiplied by some function that I already know its derivative? Final answer is that this is rather more sophisticated. We have to take the derivative of Laplace transform that we had and then multiply by minus 1 raised to the power of whatever this power is. Let's go ahead and see where does this peculiar formula come from. Let's do it one at a time. Suppose I want to figure out Laplace transform of t times f of t. Here is a simple explanation for what happens. Suppose I start with Laplace transform of f itself without that t. Well, what is that? It will have some definition, 0 to infinity of exponential of minus st f of t dt. Now, what I'm after here is a creature that looks like this. I have the same exponential, but I have also a t f of t dt. The question is, how can I force this thing to have an extra t in it? How can I force an extra t in my integration? Well, very simple. What if I take this thing and differentiate it? But I have to differentiate with respect to s, of course. So I'm going to write derivative with respect to s of the Laplace transform of f of t. That's going to be derivative with respect to s of this integral. Now we are going to do something which is to say that the derivative of integral is same as the integral of a derivative. We are going to exchange these two operations. And this issue is discussed in advanced mathematics quite extensively. For certain type of integrals, which includes all the ones that we are looking at, with certain convergence properties, it is legitimate to exchange these two. Notice that this derivative is different than that differential that I integrate from 0 to infinity and then I differentiate. Now we are emphasizing we are taking derivative with respect to s, and the notation for that is partial derivative with respect to s. So long as we understand we are differentiating with respect to s, when we want to emphasize that issue, that not to confuse it with derivative with respect to t, this is a notation that you use. Exponential of minus st f of t dt. Well, with respect to s, this one doesn't have anything with respect to s, only this one does. And the derivative of that is, well, it's every time you differentiate with respect to s, a factor of minus t comes in. So it becomes minus t exponential of minus st f of t dt. And this is exactly what we want, except that it has an extra negative. So let me put that aside, 0 to infinity of, here's my kernel, here's my function, I put the t next to f, so that we see that our function we are looking at is tf of t. And well, what is this? This is a negative of Laplace transform of this function, tf of t. And what is on the left hand side? It's a derivative with respect to s of our function. So that's going to be f prime of s. To summarize, if I have Laplace transform of t times f of t, I put this minus in front of that, it becomes minus f prime of s. This means derivative with respect to s. Well, same kind of reasoning can be applied to t squared times a function, which is going to be t times that one. When we go through that, we are going to have derivative taken twice, and that causes two negatives coming out. Two negatives cancel each other out, and I get f double prime of s. And if you want to go higher, same thing, t cube f of t. Now we are going to have 3 minuses multiplying, so we can flip back to minus, and then I will have triple derivative. So in general, if I have Laplace transform of t to power of n of f of t, this minus is going to flip-flop as many times as you have power here, so it's going to minus 1 to power of n. And this differentiation is going to be as many times as that. And the standard notation for writing that is to put that number in a parentheses so that it's not confused with power. This is not power. This is how many times you are differentiating. Okay, the formula is straightforward. Applying it tends to be rather lengthy because differentiation is lengthy, and the formulas that you have can be a little bit challenging. So let's go ahead and do an exercise. Suppose I want to find out what is the Laplace transform of t times, say, sine of 3t. I want to find this. What do? I go ahead and first remind myself, so this approach works if without t, whatever we have in our box here is a function that is known to us, meaning we know it's Laplace transform. Well, for sine, we have the answer. We had it in our table, sine of some multiple of t. That number divided by s squared plus that number squared. So we have 3 over s squared plus 3 squared. So what is this? Every time you multiply by t, you have to take this thing, differentiate once and multiply by negative. So there's always a negative as many times as you have power here. So here's power 1, I have 1. And then I have 3 over s squared plus 3 squared. That has to be differentiated once. Once, of course, we just write a prime. You don't write it like that. So the conventional notation is to write 3 over s squared plus 3 squared, then prime. Well, now we go back to Cal 1. How do you differentiate this fraction? Let me leave the minus out. So derivative of numerator times denominator, that is 0. Derivative of denominator is minus 2s. Minus derivative of denominator, which is 2s, times numerator, which is 3, divided by s squared plus 3 squared, squared. So that's the quotient rule. Let me just remind you, you come across this issue often enough. So f prime g minus fg prime over g squared, or you might write it a little bit differently. At any rate, the minuses cancel and you get 6s over s squared plus 3 squared squared. So it might be a good idea to have a separate entry in our table, just copying what we had up there. What do you think this is going to be? Would you like to pause this thing for a second, figure it out, and come back? So we recognize this 6 came out of doubling that 3, so in general I'll have 2bs over s squared plus b squared, then the whole thing squared. Now as you multiply this thing by higher power, you differentiate more, and gradually you get to have more and more complicated expression. Those of you interested in the topic, you might want to follow and try to find out what would be the formula for t to power of n. That is for mathematically inclined members of our audience. So here's a little challenge problem. Something on the side if you are interested, but that's more mathematics of dealing with functions and combinatorics and stuff like that. it's not that directly related to ordinary differential equations. Oh, sorry, carried away. So this is of course not the answer. I'm asking you to figure out if you're interested. Okay, so that is our formula number 2 here. Now we are entering a more advanced territories, more significant territories. What's the derivative of derivative and second derivative? Well, why do we need this? Because the whole premise of this is that we are going to use it to solve differential equations. And of course, differential equations are based on derivatives of the functions that you are trying to find. So if this issue wants to have anything to do with differential equation, we better have something for a derivative, Laplace transform of a derivative or second derivative, and so on. Let's go ahead and attack the very first case here. Okay, let's go after the Laplace transform of the derivative. So we are going to take a look at what happens if you have a derivative of a function and you want to find its Laplace transform. It turns out it's related to the Laplace transform of the function itself in a rather simple way. And that is what makes Laplace transform to be so useful for the solving of differential equations. So let's go ahead and see what happens in this case. Let's see. Sorry. So we want to do Laplace transform of derivative of some function. So what does that mean? It means same thing that it meant all over the place, that we are taking the kernel multiplied by the function, which now happens to be derivative of some other function, and integrate that. Well, this appearance here suggests to apply the integration by parts. So we take u to be exponential of minus st, that's our kernel. dv is going to be f prime of t dt. Therefore du becomes minus s. We are taking derivative with respect to t now, so s is a constant there, comes out, exponential of minus st dt. And v, well, I have the derivative of v, so v itself is going to be just f of t. So u dv, the integral of, so what we are using is integral of u dv is uv minus integral of v du. And if we have boundaries here from anywhere to anywhere else, we have same boundaries on the right hand side. So v uv will be exponential of minus st f of t, and this is to be evaluated between these two boundaries from 0 to infinity, and then minus v du, so that's going to be minus s exponential of minus st f of t dt. Okay, let me separate these things. So at infinity, with s being positive, exponential of minus infinity t, we expect that to overcome f of t and make it into 0. So I'll have a 0. At 0, exponential of 0 is 1, and that's just going to be f of 0. Here I have minus. Minus is plus. I pull the s outside. S integral from 0 to infinity, 0 to infinity, exponential of minus f of t dt. And that boils down to minus f of 0 plus s f. This whole thing is just a Laplace transform of f. So what we established is that the Laplace transform of derivative of a function is the initial value of that function minus initial value of that function plus s times Laplace transform of the function itself. So let's practice this. Perhaps if you have Laplace transform of t, say to power of 5, I know that that is 5 factorial over s to power of 6. Now if I go ahead and differentiate this thing, Laplace transform of 5t4, of course I can apply that formula all over again, but we're trying to practice this. Since this function is derivative of that, I go ahead and calculate the initial value of this. The initial value is just 0 plus s times Laplace transform of the original function. So that is going to be 5 factorial over s to power of 6. So that's going to be 5 factorial over s to power of 5. Now if I were to have calculated this thing from the tables we had last time, 5t4, before this theorem I would have done it like this: 5 times Laplace transform of t to power of 4, and that would have been 5 times that is 4 factorial over s to power of 5, and 5 times 4 factorial is just 5 factorial, and I have my s to power of 5. So we can do it in this problem two ways and see that the two methods give us the same answer. Now this formula is rarely used for calculating Laplace transform of some function. Rather, this is used in the context of differential equations. But before we go ahead and talk about that, let's see what happens if I have Laplace transform of the nth derivative of some function. So I could have second derivative, third derivative, and so on. And essentially what we are going to do is just what we did right now, and repeatedly apply the integration by parts and come to our final answer. So remember here, fn means the nth derivative of f. So as usual, we start with the integral 0 to infinity, our kernel, the function we are after, dt. And then we are going to use the same strategy as before, do integration by parts, and handle this thing one step at a time. So what do? We, as before, so the u is exponential of minus st. Our dv is the nth derivative of the function. Then du is going to be minus s exponential of minus st dt. And the v, well, taking antiderivative of this thing once brings us to the previous derivative. So my integral then is going to be u times v, so that's exponential of minus st f of n minus first derivative of it, evaluated between 0 and infinity, and then minus v du, minus times minus s becomes plus s, integral from 0 to infinity of exponential of minus st is what I have here, times this one, f n minus 1 of t dt. perhaps looking a little bit intimidating, but same as before really. At infinity, we always assume that our exponential kills this function, so that the limit of that goes to 0. At 0, this is 1, and this becomes minus the value of the n minus first derivative of the function at 0 plus s. And what is this? This is a Laplace transform of the n minus first derivative of the function. So that is the plan, that if you want to figure out, for example, a Laplace transform of the second derivative, something that we need in our calculation. If I want Laplace transform of the second derivative, what this says is that, first of all, subtract the initial value of the previous derivative plus s times Laplace transform of exactly that, f prime of t. So that's going to be minus f prime 0 plus s. Now, what was Laplace transform of f prime? We go to what we had, which was minus f0 plus, so minus f0 plus s Laplace transform of the function itself. So it boils down to minus f prime of 0 minus s f of 0, and s times another s becomes s squared f of s. Let's just see if we can detect a pattern so that we don't create this thing every time. So string of negatives starts with one derivative less than what we have here. So third derivative, this is going to be second derivative, then s times f prime of 0, then s squared f f of s squared f of 0. I have a typo here. And then finally s cube of f of s. So we see the pattern here. S to the power of 0 is just 1, s to the power of 1, s to the power of 2, s to the power of 3. And then, so s powers go up. Number of derivatives, 2, 1, and 0. All of these things tied to the initial values are subtracted, and the final one is s to the power of how many derivatives you have here multiplied by Laplace transform of the original function f of 0, f of s. So in general, Laplace transform of, we're not going to have immediate use for this thing, but just saying for the sake of completeness, don't worry about trying to memorize it. So we come down from this mountain, so f n minus 1, that is that derivative. Then there's another negative f n minus 2 at 0, and then f n minus 3 at 0, and so on it goes all the way down to f without any derivative at 0. Start with 1, then s, then s squared, and finally we have s to power of n minus 1 f of 0, and then at the end is plus s to power of n f of s. So perhaps a bit complicated, but that's what we achieved. So crucial thing to remember are these two, because we go after first order or second order differential equations, and we would need these. Okay, uh, no, what do we do with all of this thing? Let's go ahead and solve a differential equation actually to see what is the benefit of all the work we have done. Okay, let's go after a simple differential equation and see how we handle it here. Suppose I have an equation that looks like a y prime plus b y, and the right hand side is some function g of t. For example, it could be sine of 2t or cosine of 3t or exponential of minus t or something. A and b are some numbers, and the initial value of our equation is y of 0 is equal to some number. Let's write it y0. So a and b and y0 are just some numbers. This is some function. So here is an example. So I could have y prime plus, say, 3y is equal to, say, 10 times sine of 2t, and y0 could be, for example, 7. That's what we are after. What do we do here? What we do is, what we said, the main advantage of Laplace transform is I'm going to apply Laplace transform to this. I'm going to apply the Laplace transform to the right hand side. When I want to calculate Laplace transform of derivative, what we just learned is going to be useful, and to complete that task I need my initial value, like this f0s that we had over there. That's the initial value that I'm going to need. So let's see. First we apply the linearity. What rescues us is that a and b are just numbers. They're not functions, so we don't have to worry about them. So we write it as a times Laplace transform of y prime plus b times Laplace transform of y. And Laplace transform of a function, we said we are using a capital letter associated with that, g of s. So for example, if I had sine of 2t, I take the Laplace transform of that. I'll have, for example, a factor of 10, and you remember sine of bt would be b over s squared plus b squared. So 2 squared would have been here. Now, just right now, we learn what happens here. This is a times Laplace transform of a derivative is negative of initial value, so minus y0 plus s times the Laplace transform of y. Now, what was our convention? Laplace transform of a function, we use the capital. So it's going to be s y. So that y is a function of s, but just to prevent overcrowding, I don't write parentheses s here. B Laplace transform of y is, well, just we said is y of s, whatever that happens to be. And right hand side is my function g. So what do we do here? We find y. We find y, say, okay, a minus ay0 plus asy plus by is equal to g. Our objective is to find the function y, like here, what is the function that produces this right hand side? This is a given quantity which we find the Laplace transform of it, and then here we go ahead, and this is going to be a number, goes to the right hand side, and the rest of them I can factor. So I have y times as plus b is equal to g plus a y0. So g is some function, and this is some number. Now I say y is whatever function g is. plus a times y0 divided by as plus b. Now our objective is going to be the next level. So what happened here? So we had a differential equation. Whatever that differential equation is. We had learned previously to go straight and find the solution of it. But now we apply Laplace transform to our equation. And when we apply Laplace transform, we get to something like this. This is an algebraic equation for y. So we get some simple equation for y. We're just trying to find the capital Y. It's an algebraic equation. You notice that solving this was straightforward. Just like a linear equation back in high school algebra. We just find. So this is the easiest step. So we get the solution. So this is at least one step of this whole thing is easy. Now comes the challenging section. Well, how do I go back up? I need to apply inverse Laplace transform. The way we do that is by looking up in the table that we have and finding our way back to the solution. So we said we take this detour. This detour is called solving by Laplace method, and heavily depends on having a table and another table lookup to make the process to go easy. There's a formula for the L inverse as well, but it requires another course. We need complex analysis to make good sense of that, and we are not going in that direction. So let's see. Let's take some specific examples. So for example, here my y is going to be Laplace transform of whatever we have on the right hand side. So that would have been 20 over s squared plus 4, and then a y0, a is 1, y0 is 7 divided by as plus b. As plus b, it just comes from here. So a is 1, s plus b is 3, so that's going to be s plus 3. Okay, I have a y here, and I want to match it against my table and find out what that gives me. So let's go ahead, work on that. So I have this fraction. I can approach it one of two ways. One is add these things up and then divide, and another one is just divide term by term. There are advantages and disadvantages to either of these two. Let me take the slightly easy way perhaps out right now, is to divide this two and this two, and so it's going to have 20 over s plus 3 times s squared plus 4, and then 7 divided by s plus 3. So what happened here, if I have a plus b over c, I can just break it into two fractions. Okay, now, so the idea is I go and look at my table to see where I find this function to find its inverse Laplace transform. We are whatever y we have, that function of s, we have to match it against these and find out which one on the left hand side is the matching function. Well, very simple cases we might be able to do this thing, but oftentimes we need to take this function and break it into pieces in order to be able to actually match it against our table. If you notice up there, I have something matching this part, but there is nothing that matches to that. So I can take this thing and match it against my table up there. So this this portion we see from that table, it matches to 7 exponential of minus 3t. That's going to be straightforward. But how about this one? Well, obviously there's nothing up there that matches against this. So here comes one of the major ideas for this section. We are going to use an idea from calculus, the partial fraction decomposition. Partial fraction decomposition applies to expressions like this, which is a ratio of two polynomials. If I have a ratio of two polynomials, I can always think about breaking it to smaller, simpler fractions. What does that mean? It means when I have this expression 20 over s plus 3 times s squared plus 4, I can think that it came out of adding two fractions. One of them had this expression as the denominator and the other one had this one. They were added up to each other to create this. So these two factors come as the denominators of our fractions. Now, continuation of this thing is exactly same as the issue of partial fraction decomposition. And that is something that comes up in calculus quite often. In case you haven't seen it recently, let me just quickly go ahead and review the topic. In short, how it goes here, exactly how it was in calculus, is that if you have linear expression like this, or the powers of that, the numerator that is missing is just going to be some number we are going to be search for. If you have a quadratic or the power of the quadratic, the numerator of that is going to be linear, meaning something like some number times s plus some number. Okay, so linear and their powers, the missing numerator is just a number. Quadratics and their powers, like if I had power 2 or 3 of this denominator, the numerator of that would be always just a linear. Now what is next? What is next is to find A, B, and C. And that's going to require a little bit of algebra for us, a little bit of basic linear algebra, and I have included some software apps you might use to simplify your task in this regard. So what do? We say, if I were to add these two fractions, what would have I done? I would have taken a common denominator and then I would have multiplied these two. So a times s squared plus 4 plus this times that, so s plus 3, denominator of the first, numerator of the second. So this is as squared plus 4a plus bs squared 3bs and cs and 3c with the same denominator. So now we collect similar terms. So I have a plus b s squared plus 3b plus c s, and then what's left is 3c plus 4a divided by same denominator. So perhaps we just can write denominator and not repeat this thing. Now what? This is supposed to be identically same as that. So what does that mean? I don't have any s squares there, so this coefficient has to be 0. I don't have any s here either, and this coefficient has to be 0. All that's left is that this has to be same as 20. So I'll have a plus b has to be 0. 3b plus c has to be 0, and 3c plus 4a, okay, that's the only non-zero I have here, is 20. So in partial fraction decompositions, we always come down to a system that needs to be solved. The more crowded the denominator is, the bigger the system is going to be, the more tasks that we have to handle. And again, when this task becomes lengthy, we always use a little bit of a software or an app to help us. So here I can say b is minus a and c is minus 3b, which makes it to be 3a. I put the entries that I have here, so I have c is 3a, so 3 times 3a plus 4a is 20, so this makes 13a to be 20, so my a is 20/13th. My b from here is minus this, and my c is 3 times, so it's going to be 60/13. Okay, let's go see what happens so we don't get lost in all the algebra. So we had our y, the Laplace transform of the solution. We have option of taking common denominator and proceeding, or splitting it as it is. Either way is possible. So I left this thing alone, and that one I decided to split. So I'm applying partial fraction decomposition. We factor the denominator, and then we make fractions based on the factors, numerators. If the term in the denominator is a linear, this is just a number. If the term in the denominator is quadratic, then this is going to be linear. Then we went ahead and found a, b, c. So we had a system, we solved it, we found a, b, c. And once we have that, we have the expression for y. So let's go write y. Y was supposed to be, so we had y is a over s plus 3. So my a is plus bs plus c over s squared plus 4, and then we had a trailing 7 over s plus 3. I noticed that this and that has the same denominator, so I might as well merge them, or if we had merged them from beginning, it would have been automatically coming out as a single term. So 7 plus 20 over 13, 7 times 13 is 91, plus that makes 111 over 13. Let me write it like this so it looks a little bit cleaner. Okay, this portion is easy to go ahead in the table and look it up and see that it is some number times exponential of minus 3t. How about this one? This fraction as it is, we come across this thing quite often. As it is, it doesn't show up on our table, but when you go ahead and look at the table carefully, we see that we have s divided by, s divided by the sum of squares, or b divided by sum of squares. So we have these two combinations. So what we have to do is break this thing accordingly. So I'll do an additional partial fraction decomposition which always needs to be done. One is this portion of the fraction and the other one is this portion of the fraction, so that it shows up in our table. The first one, let me write it. So it is minus, so let me write it, minus 20 over 13 s over s squared plus 4. Is that right? This shows up in our table. That's just cosine of 2t. How about the other one? The other one, I think about it as writing 60 over 13, 1 over s squared plus 4. But that doesn't show in the table as it is. I need to have a factor of 2 in the numerator. So how do I compensate for that? So instead of 60 times 1, I write it 2 times 30. Is that right? It's the same thing. What's the advantage? Is that 2 divided by s squared plus 4 in our table. Now we are ready to write our answer. Y of t is going to be inverse Laplace transform of what I have. I'm not going to rewrite this thing one more time, but it's just that. Inverse Laplace transform of this is 111 over 13 exponential of minus 3t. This one is minus 20 over 13, and this is cosine of 2t, and this is 30 over 13, and this is sine of 2t. That becomes the answer to our problem. So problems in these sections are pretty much same style. You are going to see the first order and second order equations coming up quite often, and for the last stretches of course we are going to be practicing these ideas several times. So let's go ahead and see what happened today. We practiced the basic table. We added 4 elements to our table. One was for exponential times the function, one was power of t, or a polynomial times the function, and 2 formulas for derivatives, first derivative and the second derivative. That opened the door to actually ordinary differential equations for us. Okay, until next time, good luck and God bless.